So hi everyone. Today we are going to discuss this topic of some basic rules of the game, not really in detail, but some the game on how to analyze algorithms. Yeah. So someone has a question. Okay. So I'll move on. Yeah. So why do we want to analyze algorithm? Simply because for a particular problem we can think about many different algorithms and we would like to compare different algorithms and then decide which one is better for us and right which one we want to use. So that's why we want to analyze algorithms. And so there are many different kinds of parameters on which you could analyze. So running time is the most obvious one, that you want your algorithm to be really fast. And but there could be other parameters like how much memory, and if multiple parties are involved, then how much communication is needed to perform the algorithm, and so on. There could be many different parameters, but mostly in this whole semester, our focus will be mostly on running time. And yeah, so that will be our major focus. Okay, so the first obvious question is that why not just implement and see the running time, right? I mean, why do we need to analyze mathematically, right? So when I'm saying analyzing algorithms, I mean some formal, or I mean some mathematical way of uh, coming up with some notion of a running time and deciding about algorithms based on that, right? So yeah, so why not just implement the algorithms and see which one is performing better? So there could be various issues. So first of all, the number of possible inputs are could be too many. I mean, right? So you cannot really hope to test your algorithm on all possible inputs, right? In fact, I mean, usually the number of possible inputs are infinitely many, right? So you can't just uh, test on every input. So you could only select some particular subset of inputs and only test on that. So that's one issue. Second issue is that there could be too many algorithms to implement, right? I mean, if you are given a problem, you could come up with five different ideas, right? Even minor variations you could think of, even in one particular algorithm. So, I mean, you don't really want to implement all the variations, right? And see which one is performing better. I mean, rather it would be preferable if you could mentally analyze which variant or which algorithm is, you can hope that, or you can somehow give some concrete arguments that this algorithm definitely performs better than that algorithm, and then you just go with the first variant based on that reasoning. Yeah, so the second issue could be that there could be too many algorithms, so you can't really implement all of them. And another important issue is that if you implement it and then see the running time, it's all processor dependent, right? So maybe there are many people come up with many different algorithms and they are all implementing them on their own computers. So the running time will be highly dependent on the capacity of the processor, right? How fast your processor is and how exactly does it run the algorithm, and all those issues come up. So yeah, I mean, if you want to avoid that, then we need to come up with some way to measure the performance of algorithms, which is processor independent, right? So we don't want to get into the details of how exactly the processor will run or how fast will the processor be, and somehow we want to be independent of that, and we also want to be um, somehow independent of what? I mean, in some measure which is input independent, right? I mean, input independent in the sense that can we give a guarantee which works for all inputs, right? Instead of just some particular chosen inputs and so on. So basic idea is that we'll just think of some basic operations. So basic operations like uh, addition, subtraction, comparisons, multiplication. So basic arithmetic operations, right? So you can think of these as some kind of unit cost operations. And then we'll just count the number of such basic operations, right? And that's how we can uh, measure the running time of the algorithm, right? So that's the simple principle we are going to follow. Uh, so this, what exactly will you consider as basic operations? It is a bit context dependent. So there is no absolute choice of these things. So I mean, we'll see. I mean, depending on various contexts, we'll come up with various notions of what we will consider as basic operations and what we will not consider. Right. So any questions so far? So just to give an example of basic operations. So for example, if you have an integer array and suppose you are finding the sum sum of all the entries in the array, right? Then you can consider addition as a basic operation, right? That two integers, you can assume that let's say two integers can be added in unit cost, right? Or unit time. Um, but for example, if you are considering the complexity of integer addition or integer multiplication, right? How fast can you implement integer multiplication? Then you really need to go into the bit operations, right? So then your basic operations will be the bit operations and not addition and multiplication cannot be your basic operation, right? Because you are analyzing the complexity of multiplication itself, right? So this is just one example where you need to carefully think about what makes sense, right? So what operations should you consider as basic operations? Okay, so that is one thing. The second thing is that most often uh, our input will not be of a fixed size, right? So the input could be of any size, right? I mean, it's a variable. The size itself is a variable. So for example, this problem of finding the sum of the entries of an array, right? So now the input size is what? The input size is the size of the array, for example, and then that itself could be a variable, right? So you could get arrays of different sizes, right? So your running time is then dependent on the input size, right? So we'll basically analyze our running times as a function of our input size, right? So if input size is n, you'll try to count the number of basic operations as a function of your input size, right? So maybe your running time will look like 2n plus 3, or maybe it will look like 5n square plus minus n plus 4 or something like it. So some function of n it will look like. Um, so another issue is that this input size, again, it is context dependent. So there is no absolute way of defining what is input size. So sometimes we'll have to go into the bit complexity, like how many bits does it take to represent the input? And sometimes when it's not so crucial, then so for example, when we are looking at an array, of integers, maybe we could just take the number of entries in the array as the input size, right? So if the array has n entries, then n is our input size, right? So yeah, so again, it's something which is context dependent, and you'll get a better idea when we see many examples about, what really makes most sense, right? So what input size you should consider and what operations you should consider as basic operations. Okay. Finally, so we'll often use this big O notation. So I hope you are all familiar with big O notation. So this 2n plus 3, it is considered as, that can be written as order n, right? And instead of 2n plus 3, if we had some function like 3n minus 5, that could also be written as order n, right? So basically, this big O notation suppresses these constants, these multiplicative constants, 2 or 3 or whatever it is. And often when we talk about running time, we'll use this big O notation, that whether our running time of the algorithm is order n or order n square, or it could be order n log n, or whatever it is. It could also be order 2 to the n, exponential running time, right? So basically the point is that often we'll ignore the multiplicative constants and additive constants. And so why are we doing that? Because if we really want to worry about these constants, so they actually depend, these multiplicative constants actually depend on the implementation details. How exactly are you going to implement the algorithm? And various issues crop up. For example, suppose you have assumed that addition is a basic operation and comparison is a basic operation, right? And then you are saying that the algorithm is taking 2n plus 3 basic operations. But addition itself, the time it takes to add two numbers and time it takes to compare two numbers, these two things could be different, right? So if you really care about these constants, then you should also care about how many additions are you doing, how many comparisons are you doing, how many multiplications are you doing, right? So you'll have to go into these details if you really care about these constants. So if you just want to avoid all this, going into all these details, and really these details are not really important when we are comparing two algorithms at a high level, right? So it's just convenient to forget about these constants and just work with this big O notation. So any questions so far?
Yes, sir, I have a question. Am I audible?
Yeah. Yes.
So there are two questions. One is that, so I can understand that there can be something like n square minus n, but like
Right.
3n minus 5, is it possible that we may have to deal with something like minus n constant?
Yeah, I can't. So the question is, do we really see this 3n minus 5 kind of running time? Uh, this minus 5 you are asking about. Do we really see this? So I'm not really sure. I just wrote it. I can't think of an example where we see such negative additive constants in the running time.
Okay, so sir, one
Yeah,
more
but
question. Let
yeah.
me emphasize the importance of Vigo, but isn't it that many of the times we might have to worry more about the average case? So is there any like reason why, or is it that Bigo is actually superior than the theta one average analysis?
No, no, no. So I think this theta and big O, that's a different issue, and average case issue is a different thing. So I will come to the average case in a minute.
Actually,
Uh,
these notations are used for just measuring the capability of the algorithm. So if we are just giving a upper bound that this algorithm will not take more than that time, then it will
right,
be really good for us to measure the algorithm's capability.
right, right. Yeah. So yeah, so big O notation basically means an upper bound. One question was about the theta notation. So theta notation means it's an upper bound and a lower bound. So let me just explain by an example. So if your function fn is let's say root n. So root n is also order n because it's smaller than n. You can write order n, right? So in this case, you can say fn is order n because it's really smaller than n. I mean, it's much smaller. I mean, it grows much slowly than n, right? And but you cannot write this root n as theta n, right? So that would be wrong. So this you cannot do because theta n means that you can bound this function from both sides, right? So if when I want to write fn as theta n, that means I should be able to upper bound it by some constant times n and also lower bound it by some other constants, let's say d times n, right? So then that's when you say that it's theta n. So yeah, so big O is just an upper bound and theta n is giving a very precise bound that it is uh, also lower bounded and upper bounded by a linear function. Then you call it a theta n, theta n. Yeah, so that's all about theta. So any other question?
And sir, it could be minus, like say we are traveling n times and then the array minus 5 elements. So it could be n minus 5 there.
Right, right, sure. Yeah, yes. So yeah, so the comment was that -5 could occur. Maybe we are doing some operations on an array and maybe I don't know. In the end, you uh, so on a size n array, you might be doing only n minus one operations, right? So a minus one coming from there, something like that. I mean, the last element, probably you don't have to do anything about it, and something like that. Yeah, anyways, not a very important issue. Um, yes. So another thing I wanted to say was that we are looking at this running time as a function of the input size n. Uh, so one useful thing we get out of this is that uh, basically what we are seeing here is that how the running time is growing as the input is growing, right? So for example, if you double the input length, then how does the running time grow? Does it get double? Does it get 4 times? Does it get only multiplied by square root 2 or something like that, right? So I mean, when we do this kind of asymptotic analysis, that's what we worry about. I mean, that is what most important to us, that how is the running time growing with respect to the input size, um, right? Instead of just, I mean, it is possible that there are two algorithms, and if we just focus on some very small input sizes, then algorithm B is performing much better. But so let me give some concrete example. So let's say there is an algorithm which takes running time something like 100 times n, and there is another algorithm B uh, which takes whose time is something like n square plus 9, right? So you can see that on small size inputs, the algorithm B will perform much better, right? But for us, I mean, if you think about, um, I mean, growing input sizes, then at some point, I mean, after some input size, really algorithm A will start performing better than algorithm B, right? So this is order n and this is order n square. And again, I mean, when we use order notation, we really forget about these constants. So the point is that for sufficiently large inputs, these constants really, I mean, don't really uh, play a role. I mean, when we are worrying about how your running size is growing, when you are doubling the input length or some such thing. Yeah. So
Sir,
just give me 1 minute. Yeah, just 1 minute. Yes, go ahead.
sir, but we may not be able to always compare using order, right? So let's say algorithm having 100n and another having 50n.
Right. Right. Good question. So the question is that what if we have an algorithm which takes time 100n and another algorithm which takes time 50n? Right. So if you have such two algorithms, then definitely you'll have to look into these constants as well. Um, but as I said, if you need to worry about these level of details, whether 100, I mean, if you need to compare whether the constant is 100 or 50, then you will also need to go into the details of how many additions are you doing, how many comparisons are you doing, and when you are adding, how large integers are there which you are adding, because all these things will um, matter in this deciding these constants, right? So yeah, I mean, if it's really important to decide this constant, then you'll have to go into these details. And most often for us, we'll never really compare two algorithms which have times like 100n and 50n. Most often what will happen is we will be comparing algorithms where one has time n order, I mean, something like 100n square, and the other has time something like 1000 times n log n, right? So most often we'll be in such situation. So there we could really use big O notation.
Actually, sir, in the example which the student given, like 50n and 100n, in asymptotically we just take it as a order n, but practically they are different. But
Right, practically
asymptotically they are same.
right. Yeah, just to yeah, practically they are different, and if you really need to compare performance of two such algorithms whose running times are such, I mean, which are not very far, then probably you will have to actually implement them and see, because as I said, I mean, there is a limit to how much detail you can analyze mathematically, right? So there are some issues with, like I said, like how large integers are you adding, and these things will also play a role in these constants. So probably you will not be really able to analyze them mathematically with such precision. So then probably you just implement the two things and see. Yeah. Any other question? Okay. Okay. So now let's come to this issue about worst case analysis or average case analysis. So um, yeah, I mean, in this course, we'll be mostly thinking about worst case analysis. So what does this mean? This means that we will consider all inputs of a particular size and take the worst possible bound over all inputs of that particular size, right? So that is worst case analysis. So that basically, what does that mean? That means that, so if I'm saying that the worst case running time is n square plus 9, That means that on all inputs, the running time is bounded by n square plus 9. On some inputs, it could be doing much better, much faster. But the guarantee I'm giving is that on all inputs, the running time is bounded by n square plus 9. Now, you might say that why should we look at worst case scenarios? I mean, worst case scenarios might be very rare. And it is possible that on most inputs, your algorithm is doing much faster. And only in very few cases, your algorithm is slow. And these worst cases, I mean, these are the worst cases. So why should we care about such very rare worst cases? Um, so yeah, I mean, I don't have very definitive answer for this. So two things I would like to say here. So first of all, why not do some kind of average case analysis? So it's, I mean, this is a very difficult question, right? I mean, what does it mean to do average case analysis? So, for example, do we just assume that all possible inputs are equally likely? Uh, I mean, we can do analysis by assuming that all possible inputs are equally likely, and then um, just think about the running time as some kind of average over all inputs, right? But uh, but it's not clear if this assumption is always valid, right? So I mean, in various kinds of problems, the inputs are coming from, I mean, various kinds of mechanisms. I mean, we don't really have a say over whether all inputs are equally likely or whether some inputs are more likely than other kinds of inputs. So unless someone tells us precisely that the inputs will be coming from such and such distribution, or such distributions, such inputs are highly likely and such inputs are very unlikely, unless someone gives us that kind of guarantees, we can't really talk about average case analysis, right? And often there is no such guarantee about inputs, right? So if we don't have any such guarantee, then we don't have any choice but to look at the worst possible scenario, right? So that's one reason to look at worst case analysis. And the second reason is that most often when we look at a problem and we uh, design some algorithms, it is possible to do worst case analysis, and it is possible to come up with nice worst case guarantees. Then why not do it? I mean, if it's possible to guarantee that for all inputs you have this running time bound, then why not do it? I mean, if it's possible, right? So um, yeah, so any questions, comments on this?
Hello.
Yeah.
Sir, do we consider average case analysis only when we have randomized algorithms or in other cases also?
Yeah, I mean, it's um, a bit subtle issue. So randomized algorithms doesn't just mean that. So sometimes the randomized algorithms do some kind of random permutation or whatever. It does try to bring out some kind of average case behavior, but that's not all it does, right? I mean, randomness can be used in many other ways, right? So randomized algorithm doesn't just mean average case analysis, right? These two are very different things. And yeah, so when we talk about average case analysis, I would not really like to call it a randomized algorithm. I would just call it that when you have certain assumption, or I mean certain guarantee about the input distribution, that the inputs to your problem are coming from a particular kind of distribution, then average case analysis would make sense, right? Then you could just take average over that particular input distribution.
Understood, sir. So, for example, in randomized quicksort, our input permutations are the distribution is we assume that it's all the inputs are equally likely. So, in
Right,
that case, average case analysis makes sense.
right.
Okay,
Yeah, so
understood, sir.
this
Thank you.
this randomized quicksort, that's a very special setting where um, the randomized algorithm is basically doing what it is doing is it is taking a random permutation. So in that case, it is kind of same as average case analysis, but there are many different randomized algorithms which are doing much, I mean, which are using randomness in many other ways, right? So it's not just taking average over all inputs, right? Just wanted to emphasize on that.
But sir,
Yeah,
randomized quicksort have the worst case time as n square, because if the input size or input is duplicates, I mean all
right.
the
Yeah,
inputs
yeah,
are of same number, then it will act as a worst case.
right.
Then
Yeah,
randomized quicksort won't help us.
yeah, right. I mean, when we talk about randomized algorithm, then we'll talk about how to analyze randomized algorithms. So then we won't be really talking about worst case analysis. So we'll come to those issues. I mean, so when we this worst case analysis is applicable to deterministic algorithms. So when there is no randomness. Okay, so it's not really a correct statement to say that randomized quicksort takes order n square in worst case. I would just say that quicksort takes order n square in worst case. And I would not really make a worst case statement for a randomized algorithm. And how to really talk about randomized algorithms, that we'll discuss later on in the course.
Okay, sir.
Yeah. So any other questions?
Hello.
Yeah.
This isn't exactly a question, but I just wanted to point out, like, if you ask any online forums like Stack Overflow about this, duplicates case, all elements are duplicates. They will tell you that this case is generally should be handled by the implementation. Like, we shouldn't spend time on it. There should be a way to cancel out this case. Like, that's what they tell you. So, randomized quicksort, like, we don't really consider this case. That's what I actually looked this up earlier, because like
Okay.
it's a relevant question. That's what they say. I mean, in the implementation, we try to find a way to not have to handle this case.
Okay. So, but there is another case, right, which is bad for quicksort when the array is already sorted, but in the reverse order.
Right, sir. Yes, that's also a. But in the case, okay, right. Will that be? I was actually talking about randomized quicksort. Will that be a worst case for randomized quicksort as well? I don't remember this.
Yeah. So as I said, I don't want to talk about worst case for a randomized algorithm, right? So
Right, right.
I will how to really talk about randomized algorithms. We'll come to that later on. Okay. So this worst case only applies to deterministic algorithms. Okay. So any other questions? Okay. Okay. So let me come to my final point about how to describe or represent algorithms. Yeah, so there are two ways to, I mean, describe in the sense when I will describe the algorithms in the lectures and when you will describe algorithms in your exams. So it applies to both. Okay. Um, so basically you can describe it in whatever way. The I mean, the main goal is that you should write it in a way uh, that is, I mean, whatever is the best to understand, I mean, for the reader, right? So, that's a subjective issue, right? So, how to describe your algorithm so that it's very easy for the reader to understand your algorithm, right? So there are, I mean, two ways to describe an algorithm. I mean, one is just to write it in English, right? Say, using the text. So for example, if you are talking about a graph algorithm, and then you say find a vertex with the highest degree, right? So this you could just write it as a sentence. You don't really need to write the code for it, that how will you find how exactly will you find this vertex with maximum degree. You could just write it as a sentence. And so that's what I mean by textual description. And the other thing is this: you can represent an algorithm by a pseudocode. So pseudocode is just code, but nothing, I mean, not specific to any particular language, but it just uses the usual structures which are common to most programming languages, like for loop, while loop, a function, uh, if and else, and all those kind of things we use. And but we are not really using a precise format for a particular programming language. We are just making up our own ways of uh, representing the individual steps of the algorithm. And as we'll go on, I mean, go in the course, we'll see many examples of this. And I really don't want to define any particular way of writing the pseudocode. You can use whichever way you want it to use. It's just that it should be clear to the reader, right? So it should be clear to your fellow classmates. It should be clear to the TAs, to the instructor, and right, to everyone. So don't just use some obscure notation, right? So as long as it is one of the common notations, it's all fine. Yeah. So deciding between these two things, so there are few advantages and disadvantages. So one thing is that if you just describing your whole algorithm just in terms of a pseudocode, then that's error prone, in the sense that if you make a very small mistake, your pseudocode will stop making sense, right? Um, so I mean, so the advantage with describing your algorithm in a text format is that um, it is much less likely that you'll make small errors, I mean, some silly errors, right? So that's the advantage here. On the other hand, there might be some very tricky implementation details which could be explained only by using some kind of pseudocode, right? So if you want to really show those kind of implementation details, and sometimes those, I mean, such details are really important, so then there is no option but to use some kind of pseudocode there, right? So basically we'll be using a combination of these two things, and depending on the situation, right? So whatever the situation demands, it's just that we should keep in mind that whatever is the best way, whatever is the easiest for the reader to understand, we should follow that kind of approach. Yeah, yeah. So that's all I'll say here. Any questions before we move on? Okay.